Ничего получше работает. Так меня слышно? Так меня слышно? Okay, it works. Okay, so last week we actually stopped. We looked a little bit into Descartes geometry, la géométrie. Sometimes it's referred with French title, even in English. It was first published in 1637. Was actually written in French, which probably not the first. It's hard to claim document published in French kind of scientific book, because of course the usual scientific language in that part of the world at that time was Latin. So some Italians did it earlier, so they published some stuff in Italian.
How did the scientific language change to English finally?
Sorry?
How did scientific language change?
English? Yeah. You mean kind of common scientific language?
Yes.
No, that's much later. That's only 20th century, certainly. It's actually happened, I would say, in my lifetime. So that's, of course, very, very recent. No, but that was an important move. By the way, there is this expression vernacular. Probably you don't know, right?
Which language?
I'll write it down. I'll write it down. It's called I stopped my video. Otherwise, my okay. Vernacular languages. Just no, you may look for definition in Wikipedia probably, but it's actually how philologists and historians call local national languages other than Latin and Greek. No, basically, vernacular means not Latin, not Greek. That's rough. Greek meaning ancient Greek, of course, classical Greek. Yes, and that was a very important move at the time in 17th century. Perhaps I didn't study this question. Absolutely. It's not unlikely actually what Descartes was the first mathematical important paper written in French. All right, but I certainly know that some people did earlier in Italy with some early Italian. And that's somehow corresponds to really a booming development in mathematics and in physics, which at that point actually becomes mathematical, so to speak, right? With people like Galileo, Descartes himself, and later, of course, Newton. that I'm going to mention. So actually, so we are talking now about René Descartes. And this is La Géométrie.
On the coordinate geometry.
Sorry?
He developed coordinate geometry. X and Y.
Sorry, didn't know.
Descartes developed the coordinate geometry.
Not actually. It's not what we, yeah, no, yes and no, say. Didn't you look last week's class, no? Because I already said certain things. No, I may actually repeat a bit because I think it's never a bad idea to repeat. We don't find in Descartes anything like Cartesian coordinates as we know them today. And sometimes this coordinate A, they studied it, maybe not always, but they also thought of in terms of, say, translating geometry into arithmetic in some sense, right? So since you know coordinates, every point, you kind of translate geometry into, yeah, that was not at all his idea. And his idea actually was, not to put it in one word, was algebra, right? So, so what Descartes did, of course, he was not the first mathematician who developed some sort of algebra, even in Europe. I mentioned Al-Khwarizmi 2 weeks ago already, right? We looked a little bit into his algebraic treaty. Algebra, it basically means some rules of manipulating with algebraic rules of manipulating for solving equations. That what gave the name for algebra. Name of Al-Khwarizmi gave name for algorithm, for example. So that was very influential paper, which was translated in 20th century, in the end of 20th century, from Arabic into Latin. And then that's an important development. However, I don't quite touch upon it. It's not, I would say, it's not fully studied yet, I would say, right? There are some historical works where these manuscripts, how they went, how they developed. No, anyway, this idea of algebra, it certainly came to Europe. And I also tried to underline what it was, idea of algebra, right? And the basic idea of algebra is that you make a focus, say, on operations rather than on operanda, what you operate with. That's the basic idea that we find already in Al-Khwarizmi, right? Who basically provides pattern for, as we would call it today, solving equations, linear and quadratic equations. But then he also gives some sort of proofs or justification, if you like, of those procedures, and those are geometrical. So those are similar to what we find in second book of Euclid's Elements. Okay, I already mentioned that, right? Now then there were a lot of developments. Perhaps it's fair to say that those were some sort of alchemistry, so they were not really science in anything like Euclid's sense, right? I mean, algebra. There was very important and kind of interesting development in Italy. I kind of skipped it. There are some nice literature about that, and popular literature as well, how Italians found solution how to solve cubical and 4-degree equations, including people like Girolamo Cardano. Probably you know Cardano from You know, even in modern cars, there is some part, cardan nival in Russian. I don't know exactly how it's in English. It's a transmission to the wheels. You see, you have just one thing rotating, and you have to have wheels and how it works. Yeah, so this Cardano was extremely prolific. Actually, it's also a very beginning of book publishing. So you may now kind of see and read Cardano's book as they were published, and even those books themselves, they are, at least in library in Moscow, I kind of tried. They are very big like this. And actually, most of his production is some medicine, astrology, and that kind of stuff. And I think only one volume of 8, if I'm not mistaken, is it's kind of mathematics, mechanics, something that we would say is valuable, remains valuable unless this other stuff. Right, but again, you see, it's more like a skill. You see, some people found.
Sorry, somebody.
Okay. Yeah. So they developed some sort of techniques without actually proper justification of those techniques, right? And even it was not quite clear what it would mean to justify a certain technique, right? And there were some group of, say, people, I think in literature they called casuists, right? It's referred to some 20th century mathematicians who practice some sort of symbolic algebra. So it's actually casuist. It comes with the word from I think it's causa, which I think is Latin causa. Right. It just means thing, a thing. It's an algorithmic, basically, term translated into Latin in that way. And they introduce some kind of shorthands. Basically, those symbols were shorthands. So some sort of this idea of symbolic calculus somehow was around, right? But, yeah, talking about predecessors and the contemporaries of Descartes, something I did not actually do last week. Very important figure is, of course, François Villette. You can look, I'm bad actually remembering like dates of birth and death and that kind of stuff. So you may better check it in Wikipedia. Villette, who wrote in Latin, but that was back in 16th century. That's, I remember for sure. A booklet, usually it refers it is a goge. I think it's Latinized Greek actually. Word means basically introduction, where I think he first, it's an important figure also in algebra. If we trace it back, you know, Villette theorem, formulas, etc. However, conceptually, what I think is his really most important discovery that later used René Descartes was making connection between idea of analysis, and I will already touch upon again last week, but perhaps I'll repeat, analysis And no, I would say algebra as an art, as a technique for solving equations. Okay, so I would say algebra. Okay, I say algebra and say solving equations. And that's, I think, was really key thing for all later development, and even, if you like, for today developments. I think it remained. Yeah, okay. I explained it a little bit last time, but okay, let me equation. So what analysis means, first of all? Now, of course, we know today is a very multi-faceted term. It's very broad, and so however, was important and is today important source that tells us what is analysis and synthesis in traditional mathematical sense, if you like, right? Analysis versus synthesis. Okay, and the source is a Pappus that I mentioned, Pappus collection. So, yeah. No, I might find actually a quote from Pappus, but probably I better say my own words because it's more difficult to read exactly what Pappus said. So, no, better probably explain starting with synthesis because it's, in a sense, less problematic, I think, than analysis. And what is synthesis is basically what we find in Euclid, right? So we have first principles, somehow postulates, axioms, and we develop a theory on that foundation, right? So we looked a little bit, right? What is the structure of problem? What is the structure of theorem? And all of that is synthesis, is a kind of reasoning from first principles, which are laid out first towards certain conclusions. And that's how we build theories, right? That's all synthesis. And I'm actually contrast this traditional old distinction between analysis and synthesis with something more recent, introduced, I think, by Heinz Reichenbach, but it's often used without actually a reference because it's rather common in, say, philosophy of science and philosophy of mathematics. It's this, and I think it's it has its own limitation, but still useful for many discussion. It's called context of discovery. I could say simply discovery, right? So context just really doesn't mean much. Versus context of justification. And no, the idea behind it, it's rather simple. It's simply, if you like, an observation that to discover, say, a mathematical fact, right, or mathematical truth, or however you call it, or it could be also not necessarily mathematical, but let's just limit our discussion to mathematics for simplicity. It's one way, one thing to discover something, and something very different to justify it, right? To prove that is true, right? So it's one thing to make a good conjecture, and quite a different thing to prove that conjecture if it's provable, right? Otherwise, it's disproved and refuted. Okay, so those are apparently very different procedures, all right? And so synthesis is actually, if we analyze this distinction in those terms, synthesis belongs to context as justification fully, right? That's some first principles and some sort of logical inference, which I try to show you is very far from being trivial and even clear from a logical point of view when we talk about, say, traditional Euclid style geometry. However, it's all about justification, all about proof, right? And how then we may ask, but how those people, Euclid or whoever first formulated all this, how they discovered them? You see, okay, we may say we simply don't know because we have almost no access with very actually special and very valuable exceptions, like the letter found by Archimedes. I probably mentioned when he actually explains, he sheds some light of how he makes these discoveries. And that question particularly becomes say, pertinent in some special cases, right? Sometimes this procedure, how say, synthetic procedure, right? This reasoning from first principles looks kind of obvious, right? So you might imagine that someone just discovered it somehow in that form, right? No, if you have some, say, problems, how construct a regular triangle with a straight edge and compass, then you're right. You may say that's a solution, right? Someone think. However, this a bit mysterious process of finding the right solution works. It's arguably, people may say it's a matter of psychology rather than say logic and philosophy. So it's something very special, right? But in some cases, like in Archimedes in particular, it's particularly pertinent because that may be a further distinction which is useful. It's something amazing. If you're talking about proofs, some of those are explanatory. And that's what we arguably might want from a proof, right? Because after all, a proof, well, at least one thing that we want often from mathematical proof is somehow answer to question why, right? Why it's the case. I don't know, why there is no, why equations like x n plus n equals z, n Diophantine equations does not have solution for n bigger than 2, right? And so if we, from a proof of this conjecture, we expect some sort of explanation why, right? However, not all proofs work like that. Some proofs, in a sense, they justify the fact without actually shedding light why. And there are a lot of Archimedean proofs are like this. So we have some statements, say a cone, the ratio of cone and cylinder in which the cone is inscribed is 1 to 3, right? and then he gives a proof using this Eudoxus theory of proportions, beginning of Euclid's book 5. And it's a rigorous proof. So in a sense, it's a statement that a cone, right? If you take a cone, I think it's one of these Archimedean, and if you now have a cylinder,
there its volume is 1.
mm-hmm. Yeah. No, as I mentioned you in Archimedes, and they are not talking about volumes. No, it's equivalence in a sense what we make. Right. So I rather say this cone, its ratio to cylinder equals 1 to 3. Right. And he provides a proof, which is rigorous, which justifies the claim, the theorem. However,
without using calculus or anything. He proves it without using calculus.
yeah, wait, that's exactly no. His basic proof is not about calculus. It's in a sense translated, but actually not. Remember, we may look actually into Archimedes, but that would take time and effort. So probably we don't do that right away. No, you can do that. You can do your paper on that if you like. Huh? Go ahead. That's nice. Nice thing. Remember these Eudoxian definitions, right? What does it mean that two magnitudes have certain proportions? I may. What would it mean? A to say B is the same times the C to D. Yeah, where they are not necessarily like this, so they are not necessarily equivalent, expressible in terms of numbers, right? Now, roughly, again modernizing, but if N and M are, say, natural numbers, right, then that means that for all N and M, and if NA is bigger than MA, right, and MB, and that means basically kind of product of number and magnitude means times, right? If those just straight lines, that means that I take it twice, etc. It's more involved with surfaces and volumes, of course, and solids. Anyway, the idea is that for all such numbers, this implies, no, actually equivalent, right? Not simply implies that NC bigger than ND, MD, and no, probably the same for equality and the same for smaller, right? And if those magnitudes are incommensurable, right? If this ratio is irrational, as we would say, then that occurrence of equality is never obtained. But definition still works. That's the main trick of this definition, which allows to develop theory of ratio, theory of proportion geometrically. So in a sense, it's equivalent to our theory of real numbers. Even what I've just said, it's very actually clumsy claim. What kind of equivalence? No, those are interesting questions. So you should really look into. But in a sense, of course, right? So that's what he does. He applies that theory and provides a kind of sophisticated geometrical, purely geometrical proof for that kind of theorems. And in that sense, there is no analysis there, right? And indeed, we may say it's general question how, say, Euclid or whoever is author of particular theorem first discovered it, right? But in those cases, in those contexts like this of Archimedes, it's particularly pressing, right? Because indeed we want something like analysis which is explanatory, and this geometrical procedure is not explanatory. No, at least it's not explanatory in our familiar sense. Perhaps it is explanatory in some other sense. It is justificatory, right? So it really justifies the result. So it's quite a rigorous proof. However, given such a proof, is absolutely unclear however he could have such a conjecture, unless just kind of strike of genius or something like this, right? That's this geometrical proof has nothing to do. It's not illuminating in the sense that it doesn't give us anything like a method for solving that sort of problems. In that sense, there is indeed a contrast. And actually only in this letter discovered, let me maybe, I'm actually probably go into Wikipedia, and there is a almost criminal story with this letter, that it was actually lost during the war, and then rediscovered in some auction. That happened, I think, already 25 or 30 years ago. But then those people used this piece of pergament, but they somehow they made new forgery. Imagine. So they used this old piece of material which passed through all modern testers, so they could justify the idea that something old, but they wrote something new stuff, some foolish stuff, because they didn't believe that mathematics could be interesting for people and they would pay a lot for for mathematics. So then was a long kind of juridical case between I think it was Smithsonian Institute and some person who got it somehow, right? So that lasted like 10 or even more years. Finally, now it's in Harvard, this piece, and now they can read part of text which was read earlier by Heiberg. Part of it they cannot read, and they can read a bit more than Heiberg could read. You see, and so now that's interesting work. However, you know this word palimpsest, what it means, no?
Is it English?
Eh?
Is it English?
Yes.
I will just
The Archimedes palimpsest. No, there is no Wikipedia, unfortunately, but so palimpsest is called, it's again philological term that means a piece of pergament which is used and reused, and that was a common practice. Sorry. Yeah, so they even yeah.
Also, it's like something on which they don't erase the beauty writing.
Yeah. Yeah. Contents. Yeah, so Yeah, so in that particular document, he actually provides some explanations. That's why he's so particularly important, that he provides some explanations exactly of how he finds those results. And those explanations really are close to what we call analysis today, right? However, let's go back to analysis synthesis, to our topic, right? So to repeat, the synthesis is a justification. It's what we looked into already, right? Now, analysis according to Pappus, so we may more or less believe that it's more or less shared notion of analysis. It's actually a, as we would call today, heuristic, you know, heuristic. It's a heuristic. Do you understand? It's also English. It's come from, probably you know, Eureka. Right?
But I know the word with H.
Yeah.
E-U-R-E.
Eureo, that's a Greek verb which means search, to search. And when Archimedes, according to the language, found solution for a problem, he said Eureka, which is perfect tense of Eureo. I found it, right? So heuristic called a procedure which has to do with finding solution, right? So analysis is heuristic procedure. Yeah, and more, and what relates how that's, as I say, was on my previous slide, maybe, right? How it is related to algebra. And that, I think, is really very important thing that probably Francois Villette indeed was the discoverer, right? Probably he had some sources. It's hard to, but very likely. I don't know at least any other sources. So how does that geometrical analysis works? Suppose you have a problem, some construction problem. No, I already, I think, ask you. I recall you want to construct a rectangular triangle with a hypotenuse and a height on hypotenuse. So by ruler and compass. So what do you do? So hypotenuse C and height H C, right? So you should find this somehow that point C, right? Such that this angle, say, oof, sorry, AB, so you want it in a way that that angle is a right angle. No.
A and B are given. We want to see.
Yeah. You know how so.
We can just create a circle with that.
Yeah. So
And
yeah, right. That's not particularly different. But now think about this: how you find the solution, right? So you imagine problem B solved. It's more or less already on my diagram, right? So you imagine it's already solved. Then you recall certain facts about this configuration. Of course, this thing with the circle, you cannot simply derive it. You should guess, right? But anyway, in order to guess it, you already imagine problem solved, right? That is there, right? And then, right, then you know that that point C belongs to actually circle, which of which, say, O AB's diameter, right? So C is on that circle. So what you need to do, you need to divide AB in half, make this semicircle, say, and then, okay, made a parallel. So this is analysis according to Pappus, right? So you analyze your problem, and part of this analysis is this assumption that problem is solved, right? Problem is solved, and then you draw certain consequences from the situation the problem is solved, and those consequences actually help you to find solution, which is a synthesis. Solution is a synthesis. So that's again context of discovery, if you like, your analysis, right? And then you provide a synthesis in this Euclidean, say, manner, which we looked already into, right? Now, what is analogy with the idea of equation? No, basically, if I have a problem, what I should add to 2 to get 5, right? And I write this equation, right? It's similar, logically speaking, it's similar move where I imagine that problem is solved, right? So I imagine that X is a solution. So writing equation amounts to assuming that problem is solved. And when I wrote it down, then I tie some consequences like this one, right? So that just follows, but follows from what? Not from first principle of my arithmetic or whatever, right? But follows from my assumption that a problem is solved, right? And so all this algebraic procedure, as described by Al-Khwarizmi, if you compare it with this logical epistemological scheme, which involves analysis as a part of context of discovery and synthesis as a part of context of justification, it belongs to analysis, right? It does not belong to, so it's not a proof. And what would be proof if you simply take your theory and after all, you may say, and actually I had some experience to teach, kids in school, very elementary, and some kids are like that. They just give you correct answer. But if you try to say, but how you know this, they can't say, but they just say it correctly. And actually, mathematically speaking, I have no right to insist, because I might insist rather, right, by saying, but how you prove that your answer is correct? And actually, such a person may say, look, I just add up 2 and 3 and get 5, and that's qualified as a proof. But how this person guessed that, it's 3, it's different matter. It has nothing to do with justification. It's heuristic thing, right? So he or she has a right, I don't know, not in a sense, epistemologically speaking, right?
I think for small numbers, they can just see it. For small numbers, they can just see it.
No, you imagine that that's something very simple, but already if I'm writing quadratic equation, it's less simple, and then cubic, whatever. And you can imagine that someone just gives you answer, and that's it. That's it. So you know this Ramanujan case often. This guy, I actually should, probably it's different, right? So allegedly he just made some conjecture and couldn't prove them, right? Yeah.
He just kind of knew that it is.
Yeah. But that's different. Or probably there is some confusion here, because there are actually 2 different methods, right? If you have a person who, I don't know, solve equation, in that intuitive way without actually be capable to formulate anything like a method, it's a different situation when someone makes mathematically true statements without being able to prove them, right? Because proof for equation is a, roughly speaking, check. And all this procedure is not the proof. It's, no, at least what I'm just saying, it's kind of standard classical view on this issue, right? Now, what, so Francois Villette, at least he was likely first who noticed that analogy between this notion of synthesis and algebra, you know, and that I think was very important. And actually Descartes, René Descartes, he developed further that analogy, and actually he develops, I think, whole new ideas about everything, about logic, if you like, right? So Descartes roughly wants to justify the idea that we might not be in need of this synthesis after all at all, right? So roughly, maybe I kind of, that's kind of radical, a little bit radical reading of Descartes, which of course I would need to defend, but I think that's right in the core. It's the idea to develop such sort of analysis such that it would be so good, so to speak, right? That it would need, it would not a need of synthesis, right? You see, and that's of course, so something that's say in roughly Greek mathematics, at least for Archimedes, right, is secondary in a sense, epistemologically second, right? Maybe not secondary in some practical terms. However, certainly secondary in epistemological terms, because as I say, after all, he didn't tend to publish these things, which probably corresponds to many things which we find in mathematics today. Mathematicians may guess and come to results in many different ways, right? And in a sense, at least arguably just personal thing. It might be interesting for historians, for biographers, but not for fellow mathematicians after all, right? Because a fellow mathematician is interested, first of all, whether this certain judgment is justified, is proved or not, right? And when one provides a proof, and that's a really basis for judgment, right? Whether it's proof or not, whether there is mistaken proof, there are mistakes or not. And it's apparently quite unrelated how he or she just found that result. It's just a different question. However, the whole idea of analysis, or introducing analysis as a basis in mathematics, is to change this view, and develop kind of a procedure where this discovery and justification would come in the same pocket, if you like, right? And in a sense, what we still call mathematical analysis, no, in English it's called calculus, but in French, in Russian, we call it математический анализ, analyse différentielle and intégratielle. And that word analysis is very important there. It's very important. Right. And so in just coming to your question, Cartesian coordinates, what he does in the geometry, no, again, I recall it's actually officially a supplement to philosophical essay called Discourse of Method, Discours de la méthode, по-русски мы переводим это как рассуждение о методе. And even the title is telling, you see, that somehow method, which in traditional epistemology, something secondary. Method is a method of discovery. It simply does not belong to theoretical content, if you like, right? But for Descartes, justifies the idea to make method into the main pillar of mathematical reasoning and actually of all reasoning. All right. And this technique, and so what he does, he develops algebraic technique, right? He first introduces symbolic notation and in much more radical way than it was made earlier, because behind it now with Descartes there is a strong philosophical idea, if you like, right? And philosophical idea roughly is that I won't describe a procedure, right? I don't so much care what it is procedure with. No, I should make a reservation here. It's but let's put it as a kind of one half of truth, at least, right? That important thing is procedure. And now what I operate with less important, and that's why I can use symbols, whatever, right? And symbols roughly, they may be substituted by numbers and equally by, say, geometrical magnitudes, and probably even with something else, right? So that's a key idea. So again, key idea with respect to geometry is that we making from geometry calculus, algebraic calculus. That's key idea and nothing to do with coordinates. You see, nothing to do with the idea of translating geometry into, say, arithmetic or something. No, it's rather some kind of algebraic geometry what he's doing. By the way, even in historical works, I came across some people describe Descartes' geometry as algebraic geometry. Even in today's sense, of course, it's not the same algebraic geometry as we do today. However, it is algebraic geometry. But nevertheless, that's one important part of truth. The other, not less important, and which does not contradict, but say there is some conceptual tension between the two. And the second gives still more specific role to geometry, so more specific role. Because after all, that question, procedures are key elements now of our science, right? It's not auxiliary elements, but central. And moreover, becomes important what justifies this procedure, right? The whole idea, what it means, justify procedure is. So now we're not talking not about justification of judgments, right? But of procedures. And that's, even from today's logical point of view, I think it's quite an interesting question, right? Not just make an analogy. You probably know in logic about Hilbert style and Gensen style calculus, formal calculus. No, roughly, you may have in formal logic, you may have few rules. You should have rules because logic is kind of system where you have certain formulas and you want to derive something else, right? It's not finitary object in that sense, it's infinitary, right? However, then you have a choice between having very few rules and a lot of kind of primitive formulas, axioms. And another option of having many rules, a lot of rules, and actually maybe no axioms at all because you may have simply feed your rules with certain assumptions. That's how this calculus, so-called Gensen style, developed by Hilbert's assistant, Gensen. That's how they work. And I think that's an issue of, say, justification of rules All right, that's because you may have also derived rules. No, roughly those are just combination of primitive rules, and so you have a lot of interesting questions about rules rather than about formulas. And so we have something similar here, and of course he does not leave that question out, and his answer is roughly this, that those rules which he uses, algebraic rules, they are justified geometrically as far as we have some very clear geometrical picture of what is going on. The rule is justified. Then we may apply it outside this geometrical context. However, if we, for example, we know how to think about product in geometrical terms, and that gives us kind of very clear, as he said, clair et distinct, so clear and distinct picture of what's going on. That it means that it's justified. That means that one understands what is going on. So even if I say geometrical interpretation of operation is just one interpretation of many, on the other hand, it has this special role of foundational role. And I think this balance, if you like, between these 2 points of view determines kind of balance and interaction roughly between algebra and geometry, with which we still live actually, and which turns out very productive. So kind of origins of the story, maybe not the first origins that you can push back even earlier, you find them actually in René Descartes. So that's roughly about his contribution. Of course, no, he is the inventor of analytic. By the way, the name of analytic geometry, right? Why would we call that geometry analytic? No, now you see why, and what is real sense of being analytic. Analytic is not about coordinates. Analytic is about analysis, right? And
in that sense.
Yes, in that sense. And analysis means a method, right? That now it's not just that we prove certain theorem, right? But we have a method for solving problems. How it looks from logical point of view, that's actually a good question. And I don't know. No, at least Descartes' ambition, and actually that of some of his followers, were to develop some new sort of logic, right, based on this idea of analysis. Actually, there is this work written by one follower of Descartes. His name was Antoine Arnaud. Right, like this, Antoine Arnaud, and first name Nicole, and it's called Art de Penser, logique ou art de penser, logic or art of thinking. You see, that's again kind of different idea of logic than that we find of Aristotle. So they won't make a logic an art, and including this idea of ars invendi, as they call it in Latin, so art of invention. And this is an interesting idea. I think all that's kind of big movement towards finding better logical foundation of mathematics that will come very soon in our course, like Hilbert. They, I think, left it, in a sense, that was very conservative move, right? So they say all this stuff, Descartes and later Newton was not really well founded, right? So we should develop new logical theories. and that's, of course, was important historically, and they did a lot of important works. However, this idea of logic as a invention, I think it's kind of left behind. Probably it's kind of not a realistic dream. So we can't, of course, just go back to Descartes and all these people. However, I still believe that there is a lot of valuable stuff here. Probably we may at least use it for doing something today, right? Again. So I think that it's very interesting to look into these things from this point of view, right? But probably I should stop with Descartes because there is so many other important people around that time that we should say at least something. Yeah, one interesting thing about Descartes that he actually did not include in his geometry anything which we would qualify today as a differential integration analysis, even if historically, no, as I just stressed, these ideas, they develop somehow simultaneously. For example, we can find a lot, actually, I'm not sure if there is anything about this in Viet, but all the contemporary of René Descartes, his name you certainly know, I mean Pierre Firmat. Pierre Firmat. So again, you may look into his years. He actually, at least we find, unlike, you know, Descartes, I should stress, he was basically philosopher. So you may, of course, and probably should qualify him as a mathematician because that contribution, at least of this geometry, was enormous. However, that's rather rare example when all his mathematics comes from his philosophy in a sense. Or of course, you may say philosophy also comes from mathematics in this sense. That would be also right. So I probably should better say when his philosophy and his mathematics really go together, and that becomes successful. I think.
What was the philosophy he was working on which led him to?
Philosophy is sometimes people even call it philosophy of method. So just I uploaded there. No, I think we don't have really time to read it, but you may read this. The Discourse of the Method is actually short. It's very nicely written. It's a, you know, it's kind of French style philosophy, which means it's supposed to be literature. So it's not like scholarly things. Even Descartes wrote such scholarly stuff as well.
It's written by Descartes. Discourse of Methods is written by Descartes.
Yes, yes. And geometry that we are talking about is actually supplement, one of three. It's also a supplement on optics, it's called dioptics, dioptrics, and another on something like meteorology. Yeah. So they are supposed to be implementation of this philosophical methods, and in a sense they are. And also I uploaded, there is his earlier writing, but published only posthumously, so after the death, it's called posthumously. It's also kind of scholarly philological word for something published after the death of the author. And it's called Rules for Direction of Mind. That was written in Latin. And that is, I think, very interesting because their connection with mathematics and more specifically, say, with algebra is very explicit. So he begins with some very general kind of norms, right? But comes down in the end to, it looks like the textbook of algebra. So clearly he kind of modeled what is correct reasoning in general just after algebra. Nothing. Yeah, but coming back to Fermat, for some actually principled reason, he didn't include anything what we could relate today to this differential analysis. And even in Pierre Fermat, who, unlike Descartes, was not a philosopher. He was a lawyer actually in his life and did mathematics just in leisure time. And as a mathematician, he was much more concrete. Perhaps he was a better mathematician than Descartes, or different kind of mathematician, because he really solved concrete problems. You see, he was more pedestrian in a sense, but also perhaps stronger because.
And was he a good lawyer?
Good question. I don't know. No? Could be some sources about this. Could be. Yeah, I didn't study his biography in such a precise way, right? But he published actually something on analysis in the sense of differential analysis without actually providing any justification. So there were some sort of procedures that I may even try to remember, but I think he considered that kind of say expression, as we would say, right, where A and B say magnitudes. You may think about them geometrically if you like, right? And then I think he looked for maximum. So if you take A big, that becomes small, even negative, right? Okay, we don't count into negative. So you want to find a maximum. And I think what he does, he simply says, okay, let's replace A by something like A plus E. So you make, think about this infinitesimal, however, it's actually not how Pierre Fermat thought about it. He just didn't say anything about that. And then he called it not equation, but adéquation, some special sort of relation. So you're writing A plus or minus C. Maybe it's not important. Okay, I should look if it's going to work. EB minus, okay, B square. So so it becomes, I put AB plus BE, right, minus A square minus E square minus A, right? Now he says something like that. That's no. And now I'm saying, okay, I'm putting that sign and simply saying, yeah. And that's he called not equation, but adéquation. Okay. But then I simply take it away in that way, like this. So I'm left with just 3 terms. Then I think he divided by E. So it's it remains, yeah, so it's roughly 0 here. Then I divide by E, so it remains B minus E. No, I put it equals to A, okay? And the final step, he says, okay, I just take that away. And I have B equals to A. And this is a solution for maximum. And he doesn't actually provide any justification what's going on. Yeah.
I also cannot see.
Yeah, we may interpret. However, look, since it's supposed to be analysis, right? As I say, you're not justified to ask justification. And if you really want to prove that this is a maximum, then you simply do something else. That's actually a good question. I'm not sure that, I think in this memoir, he simply didn't provide a proof, but I imagine that he might simply have different methods for that. So he might simply not have this idea that he should somehow incorporate justification of this procedure into this procedure itself, right? Because after all, it's heuristic. You just do this.
From calculus, maybe we can justify it if E is infinitely small. E is infinitely small.
Right, and that, but I just recently, okay, I probably should work on that particular paper more. I didn't, but I just before coming here read a paper where the author says that all of this is a kind of interpretation, and in the text itself there is nothing. So yeah, probably he could also have this intuition that it is small, right? And probably not. No, anyway, it's interesting that Descartes didn't include in his geometry anything of that sort.
But it's like if derivative is 0 at A, then for small e, it shouldn't change much.
All right.
Intuitively.
Yeah.
So for small e, you can just equate them, and then at the end, you just take limit e goes to 0.
Yeah. Right. No, anyway, we may.
Wasn't invented in Fermat's time, right?
Huh?
Calculus wasn't there when Fermat was alive.
Descartes. Yeah.
This was Fermat. This was done by Fermat.
That dates, I think, to.
Fermat died on.
You may check or something like this. No.
1965. Died on
No. Actually, he read Descartes' Geometry and he replied. He's older but contemporary. Yeah, you may check his year. Everything. Yeah. No, anyway, we may qualify this piece of Fermat, right, as a part of this overall development of mathematical analysis. However, of course, kind of key figures in this development are Isaac Newton in Britain and Leibniz, Gottfried Leibniz, say on the continent between Paris and Hanover, somewhere. All right, and that, of course, is another very important piece of history. Perhaps I say a couple of words about Newton. About Leibniz is a bit more difficult to talk. Probably next time I'll try to say more about Leibniz, because he actually never published his mathematical works, and not without a reason. Okay, Leibniz. No, Newton, I'll tell you. No.
Newton also didn't publish for 20 years.
Sorry?
Newton also didn't publish for 20 years.
Newton.
Yes.
No, for Newton, the story is the following: that we have a nice text called Method of Fluxions, I have it actually here electronically. I also upload it in your right. And that was published posthumously after his death by his students, right? In there, he also develops analysis, right? What we call today differential integral analysis, in a really somewhere new form, and also in a form which makes it particularly apt for physics. Of course, it's full of kind of physical. This notion of fluent, right? Fluent, it's like fluent English, we say, right? In Latin, I think it's fluenta and fluxia. So that's roughly means continuous variable, but about which he thought as continuously changing in time. And that's, he makes some, and fluxia are, roughly speaking, derivation. So it's a velocity of how this fluent varies. All right. And this, I think those are really very strong intuitions. I have it, all of that here, but we have little time now. So probably, okay, probably today I'll give you some general picture. Next time we may look more precisely into some pieces. All right. However, it's very well written, systematic, not systematic in a special sense, because there is no synthesis, as we may say, right? It's indeed analysis. So again, it's some collection of tricks, if you like, right? With some sort of explanation, how you do this, how you do that. But there is no like first principles and something that follows from first principle. However, when he decided to present his work, he didn't publish this, right? So he deliberately didn't publish that. And he wrote another book that's made his fame and his name. And probably actually he was right not publishing this, because, and this other work is called, yes, Principia. Can you look here of public, because I always.
So I don't know the original name. In English, it's just for the Principia.
Principia Mathematica, I think, right? Principia Mathematica, Philosophia I. Naturales. I think like this. When
1687.
87, right? I should remember. That's a shame not to remember.
But he actually invented calculus 20 years ago.
Much earlier, right? Much earlier. So he quite deliberately. Look, in a sense, it was very same attitude, and also if you think about this in kind of pragmatic in terms of, say, career, right? In terms of recognition, he was totally right. He won, because I think he's the most celebrated scientist ever, even comparing with Albert Einstein or whoever. I think he ever celebrated, and quite deliberate. So in a sense, he simply considered these fluxions as a kind of toolbox, you see, toolbox that is not supposed to go to public. Probably, I imagine, I also should read more. He actually shared, of course, these ideas with some of his disciples. He exchanged letters with Leibniz. In one letter, he actually sent to Leibniz kind of hash code. It was No, I can show you. It was rather interesting story. It was a coded Latin phrase, and the Latin phrase basically said that you should consider fluens and fluenta and determine, calculate fluxia from fluent and the other way around. That is Latin phrase, what it says, but that was written as a hashtag that was coded into just sequence of symbols, which represented in some smart way, it represented the, I think, frequencies of symbols in Latin language. Something like that. So I don't know. It's actually, I think Leibniz didn't decode it, or at least it was not publicly known. And only later, that person, I forgot the name, who published actually this treaty on flux and fluency, he also decoded this message, this coded message of Newton. Right. So. And that's, I think something even today remains to be done. Of course, there is huge historical literature on Newton. It's all very well studied historically, but in terms of, say, interpretation, I think it's still open and very interesting. So it's often said that Principia is just written after Euclid's standard, but that's, of course, not literally true, right? Because it's Euclid's standard very much modified. However, I think the key idea that you should distinguish analysis and synthesis, right? And take analysis be not a proof, not justification, but just a method to find something which needs to be complemented with a justification. That's, he really stick to that point of view, right? Otherwise he would write this Principia, right? However, what is this Principia, say, from logical point of view, so to speak, right? I think it's, I've seen some work, some attempts to reconstruction. Some people, by the way, reconstruct this mathematics of Principia using non-standard analysis, for example. I've seen such things where you can really justify, but then of course it's a question, how much is it just historically motivated new work or really work of interpretation? Then I think one should be more accurate. Well, anyway, it's very, very, very interesting, right? That's it's also interesting, I find, in context of all recent discussions. Okay, I can mention it even going ahead, so to speak, about axiomatization of physics and other science, if you ever came across. That actually was one of those Hilbert's 23 problems, all right? You see some of those problems, you know, I mentioned problems delivered on the Congress of Mathematicians in the year 1900. You know what are Hilbert's problems. So one of those problems, if I'm not mistaken, number 6, you may check, was axiomatized physics. All right. So he believed he provided some axiomatization for geometry, and then he wanted to do the same for physics. And he actually worked on that himself, and that part of his contribution remains a little bit idle, I would say. Right. However, somehow question still remains in beginning 20th century, saying 20th and 30s, 1920s, 1930s, a lot of people very enthusiastic about that. After that, people became less enthusiastic, and some people really opposed that. So now there is a group of enthusiasts. Actually, I took part in a conference in summer, people who believes that it's still something to come. Some people don't believe Well, anyway, some general idea that if you're doing, say, theory of physics, you should have some logical structure and some understanding what are first principles. And so in the context of such works, I think is interesting to look in Principia, right? What kind of structure is appropriate for physics? Because there are concerns, and that's actually my point of view, that standard Hilbert-style formalism is simply not good for that. However you find your axioms, right? And of course, we can just come back to Newton. It's already time ago. However, I think that we can learn alone. I'm sorry, I think my internet, there is something.